Great. So we have like 30 people here in the audience. Can you see us?
Yes, I can see you. Can you see me?
We can see the screen, but not you. We don't see the webcam.
Oh, I'm sharing my webcam, so I'm not sure why.
I see the webcam. I see both.
Oh, okay.
So something on your end.
No, it's fine. We can see you now.
Okay, great. Yeah, ready to get started when you are.
Are we ready?
Okay. Well, thank you. So good evening, I believe, right? What time is there in Israel?
6 p.m.
6 p.m. Thank you so much for coming after your workday and listening to me speak. It's about 10 a.m. here in Texas in the U.S. I'm very honored you would ask me to come speak. I have to admit to you that I wish I was there. It's one of my dreams to get an opportunity to come someday and visit Israel. What city are you located in?
Sorry?
What city in Israel?
What city?
Israel is like one city in U.S. So it's
Got it. Well, hey, thanks for coming today. Let's get started here. So, thank you so much for the organizers inviting me to speak about this topic, SQL 16, It Just Runs Faster. My name is Bob Ward. If you've not seen me or heard me before speak at an event, this is my 24th year to work at Microsoft. I do now work in the product team, in the SQL product team, based out of Redmond, even though I live in Texas and based out of Texas. Previous to working in the product team, I worked in our technical support team. So I've had a pretty long career over SQL Server, spanning all the way back to SQL OS2 1.1. I would love to hear from anybody in the audience when I talk to audiences of old SQL stories. So if you've been somebody who's worked on SQL way back to SQL 6.0 or 4.2 or something like that, would certainly love to hear from you in an email. I have my contact information on the slide right here to get a hold of me. One thing that I love when I present to audiences, I love to do is make sure that when you walk away from this, you have these materials and demos so you don't have to remember where the stuff is. So if you look at this moniker right here, this URL, aka.ms/BobWardMS, that's a OneDrive. And if you go to that OneDrive even right now, you can find a folder where you'll find this presentation I'm doing today and any demo I'm going to show to you. So I'd love to hear from folks after I talk about these topics. So if you want to email me at bobward@microsoft.com, any questions that you don't get answered today, feel free to do that. Let me start off this discussion today with kind of a story, and that is I have a colleague of mine here in Texas. His name is Bob Dorr, D-O-R-R. He actually works on the SQL Linux project for us, and he's working support as well. So a couple of years ago, when we were building SQL 16, he came into my office, and he said, Ward, he calls me by my last name. He says, Ward, I think SQL 16 is just faster. And I thought to myself, I've got a name there. I've got a name I can run with. I can go take this concept, SQL Server 2016, it just runs faster, and I can kind of hit the road and talk to customers about this. And so this really kind of marks the one-year journey that I've been on presenting this topic, from any user conference you can name that I've been to, and I've actually traveled internationally and talked about this on this topic. So that's kind of where this story started. Bob kind of noticed by testing SQL Server and talking to the development team that we had spent some time making changes to the SQL 16 engine to make things run faster, and the whole idea was, let's do that in a way where you don't have to make any changes or very little changes to see your application run faster. So it explains a little bit high level how we got there, but what was the reasoning behind that? I mean, why would we do such a thing? Obviously, we want your applications to run faster. We're always pushing our benchmarks to run faster. But around the development time of SQL 16, between 14 and 16, we started noticing from customers and benchmarks and things we were doing that we were kind of slower than we wanted to be in certain areas. We were not able to scale and keep up with the pace of newer I/O systems, newer networks, and especially dense core CPUs. And if you kind of think about the themes that we were after, it's all about scalability. And of course, when you're talking about scalability, you're talking about the ability to push workloads against something like a database system at higher levels with higher power hardware and see faster results. I have this term I want you to learn today. I call it reverse scalability. And we saw this with customers. They would go take SQL Server, say SQL 2012 or something, and they would buy a brand new hardware system with more core CPUs and faster I/O, and they would go put SQL 12 on there, and they would push even their current workload, and performance would get worse. And then they would push higher workloads and performance would even get far worse. So instead of seeing scalable performance, they would get the opposite reaction, which is something obviously customers are not happy with and wondered why is that going on with SQL Server. So what you see and you're going to hear for this presentation today is a lot about these kind of topics, like partitioning, a very common concept in computer science to scale. It's to partition things, partition our data structures, partition files, do all sorts of concepts of partitioning things to achieve scalability, because you're breaking things down in different units of work, especially when it comes across running multiple users across CPUs. Parallelism, you've seen for many years us use queries in forms of parallelism, like a parallel query plan. Well, we've got other parts of our server, including background tasks, that we've made decisions to run things in parallel to make things run faster. We'll show you a couple of examples of that. And in some cases, just more and larger. We just looked around at something like the log writer process and said, oh, I think we can just run more log writers. Let's just do that. Let's see if that runs faster. And we just started experimenting and testing with various things to say, what if we wrote out files at higher I/O rates or higher I/O sizes and read from higher I/O sizes? And again, creating things like more log writers. And we discovered that we could get a better performance at higher end hardware by doing that with SQL Server. Dynamic response, which I'll show you a great example of, is the ability for us, instead of partitioning at the beginning of running SQL Server, why don't we make some of those decisions on the fly based on performance bottlenecks that we detect? And then finally, improved algorithms. We just have parts of the engine that, quite frankly, in SQL 16 we took a look at and said some of the algorithms we were using even dated back to SQL 7.0, which was fine back in 1998 and the early 2000s for the hardware systems that existed then. But those algorithms just couldn't keep pace with what was going on with later hardwares. And a great example of that is like a spin lock that we use, this concept called spin lock. And then we would go to the team that built in-memory OLTP and said, how did you make that thing run really fast? And they said, oh, well, we have techniques that we've developed where we know how to do things in a no-lock fashion that don't require spin locks. So that's kind of an example where we would go internally into the engine and create improved algorithms. So that's kind of setting the stage for what we're doing. Now, nothing we built was intentionally designed for Enterprise Edition. You may have seen us announce in SQL 16 SP1 that we kind of lit up several features that come with SQL Server so that they run in Standard Edition or even Express Edition. But from the perspective I'm talking about today, we made no design decisions for what I'm going to show you just based on Enterprise. So a lot of things I'm going to talk about today exist in Standard. Some of the things, if I do mention something that exists only in Enterprise, it's just because that feature was there, but it's not because our intentions of making things run faster were only for the Enterprise SKU. So before I get into some of these core engine details, what I found as I went on the road and talked to customers about this concept is that a lot of customers were kind of missing out on a couple of key features that we added in SQL 2012 and in 14, and of course exist and are improved in 16 and coming in 17. And these are it right here. That's column store indexes in in-memory OLTP. And these numbers that I show on the right-hand side are not just made-up numbers. Those are proven numbers with customer workloads we've seen using these technologies. So if you walk away today with a concept that you're going to go research and take a look at, if you have not made any investments in looking at column store indexes or in-memory OLTP, please take a look at that because, again, we've enhanced those even in SQL 16, but they've existed even in older versions. And substantial query performance can be achieved by using these technologies. But this is kind of my list. When Bob Dorr came to me and decided to embark on this venture of the SQL 16 just runs faster concept, one of the things that he did was create a blog series. And we have this blog. You can just search on the internet for Bob SQL, just that word, Bob SQL, and you will find our blog. And this list that you have on the screen, and there's actually even more, is a series of blog posts we have done on all of these different topics. There's no way I could actually do that in a 1-hour session. So I just picked and choose a couple of these topics to show you. But here's the good news. If you see something on this list that you're like, whoa, I wanted Bob to talk about multiple log writers, but he didn't have a slide on it, at the back of the deck that you, again, can download from this website, aka.ms/BobWordMS, I have a slide on every topic. So at the end, you'll find something called bonus material where you can go back there and take a look at a slide of anything that I don't cover today. So a lot of different topics covering a lot of different parts of our engine, anything from just the core engine to spatial, to always on availability groups, to temp DB, you know, IO systems, you name it. But we're going to cover several of these today. And in fact, let's talk about that and talk about core engine scalability. You know, I actually have an interesting story for you. I traveled when I was in the support team in 1998 from Texas to Seattle to participate in some beta work for SQL 7.0. These are the days where David Campbell ran the storage engine organization, and the SQL development team was much smaller. But back in those days, if I was actually doing testing on a machine that was 8 processors, an SMP type machine of 8 processors, well, I thought I was in heaven. I thought I had the best computer in the world at that time, right? And if you looked at the evolution of SMP machines, they would grow in number of CPUs. That was how things got, you know, scaled out. Was it grew to things like 32, and that was kind of the max of some of these older machines. But what happened in those environments is bottlenecks started occurring at the hardware level, specifically at the memory bus. All these CPUs trying to attack the same memory bus to get memory. So that was kind of a problem, and thus born this concept of NUMA, non-uniform memory access. And if you've not seen NUMA or used it, you know, it's kind of a computer within a computer. And the good news is that SQL 2005, out of the beginnings of that design work, was designed to have NUMA built-in capabilities. In other words, we recognized we would run on a NUMA machine and we would take advantage of that. And you're going to see like this concept of partitioning come into play a lot of times, where we'll partition things based on NUMA nodes. Well, the original NUMA design of these machines, most of them had no more than 8 logical processors per these nodes, so everything was kind of great. But then came along multi-core and dense core technologies with hyper-threading. And in fact, today, this slide's probably even out of date. You know, you can get CPUs in the market now that are not that expensive with 24 cores within a single processor. Of course, at hyper-threading, that makes them 48 logical CPUs per processor. And a lot of those systems, each processor is its own node. So now what's happening is the same type of bottlenecks can occur at the node level as occurred at the computer level when you were running, you know, more than 8 CPUs per a given node. So for example, we have this concept I call spin locks, which we still use in the engine, even though in some places we've replaced them. They don't scale well in these scenarios when you've got a large number of CPUs that exist per node. So here's what we did in SQL 16. In SQL 16, we can't change the hardware architecture, but we can change SQL Server's perception of that architecture and making some of our partitioning decisions. So by default, just by installing SQL 16 or upgrading to SQL 16, when we detect more than 8 physical processors per a NUMA node, we split them, we partition them. Now again, we're not changing the hardware level information at all, just SQL's view of NUMAs for scheduling purposes. We will partition these, and we're always going to try to align things on kind of as close to 8 as possible to get that kind of magic number. So you might ask, you know, well, why do we actually do that? Well, I mentioned before that with this NUMA technology, we make partitioning decisions in our code for certain data structures and various things. So by having more NUMA nodes, we actually get a boost in performance because we have more partitions. One example I listed here is something called an IOCP worker, which is our IO completion port worker. That is the background thread that accepts connections and queries into the engine. And we build SQL Server to have 1 per node. Well, if we have more NUMA nodes, we have more of these workers. And so theoretically, we can get a boost in connectivity and patch throughput. And you know, a lot of these slides you're going to see in here, I've given you some numbers that we've seen from certain customer workloads. Notice that final point there. We've taken workloads that are derived from our TPCE benchmarks, and just by putting them on SQL 16, using AutoSoft NUMA on these dense core machines, we can get a 25% increase in performance. Now, for you in the audience, if you're thinking, can I just slap this on a new machine and just boom, SQL will partition, it works great, you can, but you're going to get a better boost in performance if you got one of these more denser core CPUs on the market, something that goes way above 8 and allows us to partition it in a much more granular level. So I thought it might be helpful for you to look at this kind of visually. You know, what's this going to look like when you get one of these machines? So you can see here at the top, this is a machine in the labs in Redmond, kind of a typical machine I've used before, and that is a machine with 4 sockets, each having 18 cores per socket. But at hyper-threaded, that's 36 logical CPUs. So across, and each socket has 1 node. So across the nodes, you have 144 CPUs. So at the hardware level, this is kind of how you look at it visually. Each number is a logical CPU ID. And the reason I listed it this way is if you look at that vertical bar, CPU ID 0 and 1 make up one physical core. So why is that important? Well, SQL will look at this environment here. Remember, we're looking for greater than 8 physical CPUs, which is 18 cores here in this case, 8 physical cores. So we will break it up like this. We would take this 36 CPU environment, and we would break this logically in SQL Server into 4 nodes for one node. But the numbering, if you look on here and pay attention to it, it's kind of interesting. Notice we don't go 0, 1, 2, 3. We do this very intentionally. What we're trying to do is we're trying to avoid putting 2 logical CPUs from the same core on the same node. And the reason is this is all about scheduling our worker threads. Now, it's possible that you can eventually have worker threads scheduled across all of these, but why not out of the gate try to do everything you can to avoid putting work on the same core at the processor level? And so that's how we divide up these CPUs in this kind of odd even type environment. And notice also that we didn't take CPU 1 and put it over here on node 1. We actually skipped all the way to 18 because when we do things like degree of parallelism for queries, we just start at node 0 and we just start scheduling across nodes, node 0, node 1, node 2. So you can see that if a given parallel query did not exceed node 0, node 1, again, we would avoid any core contention by running on these nodes. We can't hide from the fact, though, that the hardware level, this is still a memory node for NUMA. So SQL does not discount that. And in fact, if you look at the dynamic management views in SQL Server, these are all still associated with the same physical memory nodes. So if you look at DMOS nodes, you'll see 4 nodes here, but you'll see that the memory node 0 still takes place. I've got a great blog post that I did after I started presenting these series that show you bitmaps and various types of examples, kind of what this looks like. So that's AutoSoft NUMA. Any questions you have about what we've done here with this technology?
No.
Okay. So that's AutoSoft NUMA. Again, out of the gate by default on SQL 16, it just works. You can turn it off with Auto Server configuration if you think there are issues, that's something you want to do. I have not had a single customer, now SQL 16 has been out for a year, I have not ever seen a single customer complain or have an issue with this technology. I've only heard customers come to me and say, hey, I actually am seeing a boost in performance because of this. And one of the points to note in this more detailed link I have here, this also works in virtual machines. However, the virtual host presents to SQL a node configuration. If it presents CPUs to be greater than 8 per node, we would actually partition even on a virtual machine. Okay, so I mentioned about this concept of a dynamic memory response, and this is a great example of what we've done. For the longest time in SQL Server, we've had this concept called a CMem thread weight, and you might have seen this in your environment. And a CMem thread weight is nothing that you can control in your application. What goes on in SQL Server is if you think about the memory that we use in SQL, the majority of memory today comes from the buffer pool for database pages, or it comes from plan cache for procedures and ad hoc queries, and then maybe it comes from in-memory TP or column store or some of these other technologies. But SQL Server, because it's a database engine, a multi-threaded database engine, it has other memory needs internal to the engine. And if you're a developer and you have to allocate memory within this engine for multiple threads for these data structures that are different than your data, you have to find a very clever way to do that. And if you're say a Windows developer or even a Linux type developer, you're going to use some built-in memory management technology libraries than doing it on your own typically. Like in Windows, you might use a concept called a heap, right? You would use the heap manager in Windows just to allocate 100 bytes here, 1,000 bytes here, whatever you want to do. Well, when you do that in a Windows environment, Windows by default will provide a thread-safe environment so that no one thread can tamper with the internal linkage of these memory allocations and deallocations. Because remember, if you're allocating memory in different sizes across these threads, somebody has to internally track all these allocations. Because if you allocate 100 bytes and another thread comes along and has to deallocate those 100 bytes, there has to be a tracking system to make sure this all works correctly. So again, you have this concept called thread safety when it comes to this. In SQL Server, we built something called a memory object. That's a very similar concept to using this thing called a heap. So that our developers that build a SQL engine don't have to worry about some special Windows library. They just use this abstraction called a memory object. And SQL Server, under the covers, handles memory objects by default. Well, some of these memory objects are global. And so, and they're global in the sense that multiple threads may need to access them. So if a lot of threads have to come and access these global memory objects in a very scale type way, you can run into performance bottlenecks. And when that happens, you see something called a C mem thread wait. Now, we use this partitioning concept. I mentioned that before as a scalability concept, that some of these memory objects are partitioned automatically by node or by CPU, therefore helping avoid these memory bottlenecks. And in fact, maybe you heard this trace flag 8048. If a memory object was built to be node partitioned, this trace flag will automatically promote it to be a CPU partition, to therefore create better scalability. But very few memory objects are built that way out of the box. And that's because it requires overhead to partition things by default. And what would happen is, over the years, every time we would find a customer that really has a bottleneck of the C mem thread wait, we would have to go create a hotfix. Like, I remember being in support for a period of like 5 or 6 years, 2 or 3 times a year, somebody would complain about this, which wasn't their fault, in some scale environment. And we would go create a hotfix, and the way the hotfix would work is we would just go partition a specific memory object to make it more scalable. Well, that's a little bit, tedious to keep just doing this. There's got to be a better way. And so here's what we did in SQL 16. We created a dynamic system that once we detect a scale problem or a contention problem with a C mem thread wait, we will dynamically on the fly partition the memory object to a node level. And then if we detect that there's further contention because we partitioned the node level and that's not good enough, we will promote it to a CPU level. So we do this automatically. Behind the scenes, you don't even know what's going on. And in fact, the behavior could look like, if you're paying attention to something like DMOS waits, where you start seeing C mem thread waits in your system just briefly, then all of a sudden they just go away. Like you don't see them anymore. And it's pretty amazing. This chart here kind of just shows the scalability, the green part being the batch requests per second going up, and the red being the waits going down to 0 as we kick in the system. And it just works. And we've seen 3x improvement in memory allocation with less CPU overhead to do that. Well, it's really interesting, but why don't we see this in action? So can you still see my screen okay?
Yeah.
Perfect. So I've got a perfmon chart for you. And again, all these demos are available for you when you download this website. This perfmon chart shows you 3 perfmon counters: processor time, batch requests per second, and something called thread safe memory object waits per second. So this is the same thing like a C mem thread wait. So I'm going to kick in this workload. Well, first of all, here's kind of a funny thing for you, is that I have this script right here in my system. Because this kicks in so quickly, I'm going to have to turn on a trace flag that will disable this functionality. It's an internal-only trace flag, but that's because we only use it for testing purposes. So I'm going to turn off this functionality so you can see the behavior, and then I'm going to turn it back off so that you can see us actually fix the problem. If by default, this would just solve itself automatically. So let me run this workload here. And if you go into perfmon, what you're going to see is a high CPU utilization kick in at the top here, almost to 80%, level up around 60 to 70. And you're going to see our batch requests per second kick in around 2,900. And notice that the weights themselves get pretty high, right? Let me just see, make sure this is still working. Okay. So all of a sudden, you can even see our batch requests per second kind of get, let's see, I think this workload, let me see what happened here. No, I think it's still running. This should have kicked back in as a wait scenario. Let me go back and run this again and see what happened. Okay. Let's see this again and see what happened here. Let me restart my server real quick here. Okay. Let me kick it back in. Okay, let me go back and turn this off. And let's clear this window here. And let's go run this again. Okay. So what I expect to see happen is, again, batch requests per second kick in, and these waits get much higher. Oh, it's still not working. I'm not sure why. I've done this demo 100 times, I promise you, and I've never had this happen. Don't know what's going on. Let me see. while I'm trying to get this to work, does anybody have any questions for what I'm trying to show you here? I think the server's crashed, actually. That's not good. Wow. Yeah, this is really interesting. So I've crashed SQL Server successfully. That's really interesting. I'm going to give this one more chance, and if this doesn't work, we'll just move on. Let's start SQL Server.
Share the same instance?
What's that?
The same instance?
I'm sorry, I didn't understand you.
Are you using the same instance for the workload and for the traceback?
Well, this workload is just running an extended stored procedure just to kind of show the behavior here. I don't know why that did not work. Hold on a second here. Let's make sure recovery is completed for everybody. Okay. Let me refresh. One of my databases is still in recovery here. That was running. So I'm going to turn this trace flag on. Let's try this one more time. Yeah, I don't know why it's not working. This is immediately crashing as soon as I start running this, so I cannot explain that. Let me go and move on. You can certainly run this demo yourself. And back to showing this chart, the behavior that I show here is the fact. Let me show the screen here. The behavior that I show here is the following, and that is that you have SQL Server batch requests per second that run at a certain level. And the red line indicates the waits that are occurring. And then we dynamically respond to these waits by promoting these memory objects to CPU level partitioning. And so you have no more waits at all. They just go to 0. And you see the batch requests per second get really high. And if you go back and look at my, yeah, I've actually killed SQL when I'm running this thing. I don't know why. That will be an interesting debugging exercise for me afterwards to find out why am I killing SQL Server. It's the actual procedure I'm using is actually crashing. But back to this perp chart, what happens here, you see the CPU level be really high right here. What happens is once the memory objects weights go down to 0, your batch requests per second, you get like this 3x boost in performance. But the more interesting aspect is that the processor level performance goes to almost nothing. And the reason why that occurs is because we use spin locks to protect these memory objects. Well, if spin locks are protecting them and we have less weights going on, we have less CPU, because when you wait on a spin lock, you actually burn CPU doing that. So it's an interesting observation for you when you look at SQL servers. If you ever have unexplained CPU usage at a high level of SQL and you don't know why, because you don't observe that from your queries, it could be you're having a spin lock contention problem. And that's the kind of the nature of what that actually looks like. So apologize for that demo not working. You yourself can go run this after the fact and you can see my instructions about how you would actually see that behavior. Let me restart SQL because I'm going to need it in another demo. So that's dynamic memory object response. And again, one of the things I love about showing that slide right there is that this is all happening behind the scenes. You don't even really know what's going on, and it's designed to kick in and heal SQL Server for a contention scenario that you may see in the past. You would see it, you have to troubleshoot it, but now we would just kick in this behavior and fix the problem in self-heal SQL and file from a performance perspective. Let's talk about parallel redo, another great feature behind the scenes in SQL Server that is kind of one of those things that I like to view it as. It's there when you need it. So if you know anything about SQL Server recovery, we have to do recovery in 3 phases. We analyze what's in the transaction log, then we go back and we redo committed transactions that basically, of course, where the page in SQL Server does not reflect what's in the transaction log. And then we have to undo transactions where the page does reflect the change that has to be rolled back. So there's 3 phases. And if you think about redo is typically an IO-bound operation for very, very many years. And the reason is that all redo is doing is reading a page from disk from the database, loading into cache, and applying committed changes from the transaction log. So reading these IO pages is IO intensive, right? And if you've got a fairly slower IO disk, that's your bottleneck. So SQL Server doing redo as a single thread is never an issue because we can't do things faster than we can read these pages from disk. Well, with faster I/O devices, this is not the case anymore. As we're reading these pages, you know, the page is coming very quickly. We discovered we're not pushing the CPU very hard from a processing perspective to go apply these changes. And then we have these scenarios where we have availability groups that require secondary replicas, and we're always redoing there. So we want that to be as fast as possible. So what we decided to do was use that concept called partitioning that I mentioned to you. And when we do redo now, based on your design, we can go take standard workers from SQL Server Worker Pool, and we can dedicate them for something called redo work. And the actual command that you would see in the SQL DMVs is called parallel redo task. So what we do in SQL Server is we build up something called the dirty page table as we're analyzing the transaction log. These are pages that we know need to be modified from committed transactions based on the transaction log. So we got to load these pages up, but now we're going to do this and we're going to work on these pages in parallel. So we assign these pages to the dirty page table because we know we've read it from the transaction log. We build this up, and we're going to assign workers to go after each of these pages. Now, you might notice something very interesting in this design. Each worker in the redo scenario can only go after a given page and then apply the log records in what's called log sequence number order. And the reason to do that is to make sure things are consistent. We can't have one worker work on a given change for a page and another worker go work on a different change for a page concurrently because we might conflict with each other. These log sequence numbers have to be applied in consecutive order, or else we'll throw the consistency of transactions out of sequencing and have failures. So that's how we do it. We take the partition table, the dirty page table, we partition it by page number, and then each worker is assigned in a queued fashion. Hey, you go work on page 1, page 2, and page 3 accordingly, and then concurrently just apply these changes. And then when you're done, go work on the next page, etc. So we're able to get great processing on this and great throughput by partitioning the table and allowing these parallel workers. There's a limit to these workers. We don't just allow this to go out of control. In fact, we do a max of like 16 workers per database if we're running recovery. Because remember, recovery runs in parallel, multiple databases at one time. And then we allow like 100 total for the instance of running recovery. And here's the numbers, 80% increase in standalone recovery in SQL Server. Let me show you that in a sec for a little bit here. Instead of actually running a full demo, what I've done is I've actually shown you another interesting feature of SQL Server in SQL 16. We use this X event technology to allow you to trace database recovery on a given database. And so what I've got here is I've got an X event file first showing you what it looks like to do serial redo of a database. Now, just like the previous demo that I showed you, there's a trace flag to disable parallel redo just so you can see this behavior, because by default, we're going to kick this in on your database. So this database recovery trace event records each sequence that's going in recovery of this database that I have here. And you'll notice the timestamp for this redo phase right here is way back to January this year. So January 11th at 9:43 p.m. at 22 seconds, I started reading. And if you scroll down and look at these trace events, you can actually find about 16 seconds later, which is 43 at 38. So 16 seconds it took me to go redo this database, which isn't all that terribly slow. But you can imagine for a very large number of committed transactions on a very large database, and you may have seen this before in your system, this could take minutes of time or even longer than that. So what does parallel redo look like? If I didn't use the trace flag on the same workload, the same database, I would do something like this. I would look over here at 9:35:59, I started redo. If you look back up a little bit, though, you're going to find something interesting in this trace. You're going to see that we have these messages that will show up now. The parallel redo manager shows multiple redo workers starting up for this database. That didn't show up at the previous trace at serial level. So if you show here, if you go down here at what started at redo, we'll scroll down here again. I started here at 59 after the hour. And if you see about 10 seconds later, I now finished redo. So I have 10 seconds versus 16 seconds. And you're probably sitting back going, that's not very exciting. But that is just an example of the throughput example for a small number of transactions on a database. Again, imagine if I had to amplify this for something that takes 30 minutes or 20 minutes. Now that is shaved down 80% of that. It could take even a couple of minutes versus 20 or 30 minutes because we're running everything in parallel. So that's that kind of functionality. It's on by default for SQL 16. And again, take a look at this database recovery trace extended event if you'd like to learn how to trace more for SQL Server recovery scenarios. On by default, 80% boost in performance, and it really can make a difference with an always-on availability group for secondary replica redo purposes as well. So if you're not using availability groups, you may say to yourself, you know, why do I care about this? Well, you care when you have to restart SQL for some emergency production scenario, and you don't have to wait for a long period of time for redo to happen in SQL. So let's move on and talk about DBCC. Maybe it's been a topic of interest of you in running CheckDB in your environment. If you look back in the past of SQL Server, running CheckDB on a database as we got really large database systems and really large databases became a lot slower for customers. And I worked on a project around SQL 2008 timeframe where we were able to go in and make some changes to something called a multi-object scanner latch, this internal latch we would use to coordinate synchronization of parallel workers running CheckDB, reading in these pages. And we got some performance boost out of doing that for very large database systems. Our focus at the time was CheckDB with physical only. And the reason is that we knew with physical only we could make a bigger difference than a full CheckDB, because a full CheckDB has other factors that affect its performance, like how many indexes you have, how big are the indexes, all these logical checks we had to do. But the physical checks are more of just about reading the pages in from disk and just doing a quick audit on these pages to make sure the pages themselves are okay. And I have this kind of an interesting test I use when I look at CheckDB performance, and that is what I call the backup to null test. Notice the word null is in single quotes. That's not a typo. Maybe if you've done this before, you've never seen it, but if you do backup of a database to a disk called NUL, you're not writing to anything. All you're doing is having SQL Server read the database pages from disk and in the backup case, and then do nothing with these pages. So effectively, it's an easy way to test how fast can SQL read pages from a disk using this backup to null. And so I told the developers, we need to make CheckDB with physical only as fast as possible, as close to that test. And so in SQL 2008, we were able to get pretty close to that, actually, a much better number than we had before. Well, in SQL 16, as we were building it, the developers that worked on the in-memory OTP project took a look at this code and said, you don't even need this latch anymore. We can use this concept called a no-lock approach in our algorithms to go check pages. And I think we can even push reading pages and processing even faster. So the results are pretty staggering. If you look at a database of like a 1 terabyte database that we call an SAP database in quotes from the SAP company that uses SQL Server, it's a database with a lot of tables in it. Just by taking an SAP database, upgrading to SQL 16, we could get 7x performance boost with CheckDB with physical only. But and the more degree of parallelism, the better performance that we would see in running this workload. But even a small database of a few tables at 5 gig level, I could even get 2x faster performance. So this chart is really interesting. The chart is showing the duration of running CheckDB as you have degree of parallelism. So you can see the red bars are the old approach. And this is a great example of reverse scalability. As I pushed a workload harder on higher CPUs, I got worse performance. But notice the orange bars represent how well the new approach is able to keep up or even get faster performance with more parallel workers at a higher level. So again, 7x performance out of the gate on a 1 terabyte database for CheckDB. So as you see, I'm just kind of skipping, I'm going through a couple different topics that kind of cover the gamut of what we're doing. Again, if you don't see something that I'm covering on the list that you saw on the first slide, I've got bonus material for that. So what about TempDB? You know, I think that's been one of the most common topics I've seen discussed from customers over the years with SQL Server as they use the product. And that is, how many files do I need? And what are these trace flags that you guys have created to help me figure out how to allocate a space in these files? Well, one thing that I want to make sure you understand is that this is not about I/O. When I talk about building and using multiple data files for TempDB, in a way, when you do that, you are creating a partitioning scheme for SQL Server. That's because in each data file, we must have these allocation pages for creating space, for allocating space for SQL. The GAN, SGAN, and PFS pages, they control, effectively, they're really data structures on a page that control where is the space for pages on these files. You know, where are the uniform extents, where are the mixed extents, and then which pages are allocated or not allocated. So accessing these pages is like accessing data structures for multiple threads, and as we've already described, if you have things partitioned, you're going to get better scale performance. So the more files you create, the more partitioning you're building for SQL. Well, you can get a little bit crazy here where creating too many files doesn't really make sense. And in fact, I did a talk at the PASS Summit back in 2011 where I did a little test and kind of proved that, you know, creating one data file per logical processor up to 8 kind of makes sense, and then kind of add by 4 until you don't see any performance benefits anymore. So in SQL 16, we did something really interesting. Instead of making you figure this all out, why don't we create some defaults out of the gate when you install SQL Server, and then during the setup process, give you the ability to configure this without doing it after the fact. And so when you look at SQL 16 setup now at a setup screen, we have a new TempDB tab where you can pick the number of files, the initial size of the files, the auto-grow intervals, how do you want to spread these across different directories or drives, the size of the log, and the auto-grow of the log. These are all things that you would never get a chance to configure before the SQL Server. So yeah, you can kind of see how we do this, but we do some defaults. So again, based on the premise that we built that it's 1 per logical processor up to 8, that's the default number. If you were to install SQL Server on a machine with 8 logical processors, you out of the gate would get a configuration that looks like on the screen. And it's even conceivable that you could do this out of the gate and never even need to configure SQL Server's TempDB any further by just letting the defaults take place. But if you wanted to, you have the ability during setup to do that. And we allow very large sizes. In SQL 16, we kind of restricted the size of this, but in SQL 17, we bumped this up to even be 256 gig per file if you wanted to. So why does that even matter? Well, this is that chart that actually I pulled out of my PASS Summit talk in 2011, and I kind of dusted off the repro I used. And on my 1 CPU 4-core hyper-threaded laptop, I can take SQL 14 out of the box with no changes to 14. Just install it. SQL 16, just install it. Don't make any changes, and I can get a 2x boost in performance just by doing that. Because SQL 16's default configuration is much better than 14. Now, if you configured 14 the right way, you would get equal performance, but it just shows you that out of the box configuration for 16, without making any changes, you get a boost in performance. And in the back bonus slides, I have comments about these trace flags. Like this trace flag 1118 is used for something called uniform extents. And I show you that with and without the trace flags and the number of files, you can see the actual duration and the boost in performance that you get. Now, these trace flags no longer are needed. We just put them on by default for you. So another example of just putting something on default, you don't worry about it, and we make TempDB performance run faster out of the gate. And again, 2x faster performance out of the box experience, even on a single 8 CPU machine laptop. Okay, let's talk a little bit about I/O. I think we've done some interesting things here at the I/O level that you'll find interesting. So one of them is something that's been around a while, and that's instant file initialization. And if you think about how you create databases and create files, the speed prior to this feature in SQL 2005 was as fast as we could write zeros to the disk. But Windows gave us this new concept of telling the Windows system, here's the length of my file. I don't want you to have to write zeros to expand the file size. You just figure it out. And Windows has that ability. You tell Windows, let me have a 100 gigabyte file. It comes back immediately and says, oh, here's your file. What it does in the disk is it just reserves that space for you, but it doesn't actually allocate and write the zeros in there. So the speed now of creating a database with this concept is almost the same regardless of the size you're doing. But who really cares about create database? I mean, I can create a database of 10 gig on my laptop, and even though previously it took 5 minutes, I'm only doing that one time. I'm not doing that often. But you certainly care about restore and auto grow. So anytime we restore a database, we have to go create the database file. And so you don't want that to take a long time. And then anytime if you have to have the database file auto-growed, you don't want that to take a long time either, because it could be holding up major, it causes a major blocking problem and hold up transactions. So you certainly care about this functionality in this restore and auto-grow scenarios. So using this functionality is very important. And the way you use this functionality is you take the performance volume maintenance task from Windows privilege and you assign that to the SQL service account. When you do that, we automatically use this functionality, and creating databases and restores and auto-grows for data files are very quick. And the only catch here is that anyone who has that privilege could see the bytes on the disk that was previously there. It sounds like a security problem, but if you think about it, it's only people that have that privilege, which are Windows admins by default, or anybody these admins assign the privilege to. So it's controlled by a Windows admin functionality. But anybody else that didn't have this privilege would actually see zeros on disk. Now for the transaction log, we can't do this. We can't use this functionality because we must rely on a known byte pattern to know the end of the log, which is why we must actually initialize the transaction log. So you're asking, well, what did you do in SQL 16 that's so interesting here if it's been around since 2005? What we did is we put now in the setup screen where you configure these services a checkbox to turn this on. So you don't have to go scrambling around and figure out what Windows program do I have to use after the fact to do that. And the other thing we did that's interesting is we enabled the service SID for this privilege. So even if you go back after the fact and change the actual service account for the database engine, it doesn't matter. We'll always have this privilege turned on if you check this on by default at setup time. The new installer that we provide for Developer Express and Evaluation Editions, it actually turns this on by default. So 200% faster, by the way. You can take an easy database demo on your laptop if you want to. Let's say a 10 gig, a good one's like 10 gig. Take a 10 gig database file. Don't use this functionality. See how fast it is. Turn it on. You'll get a 200% boost in performance just by doing that. And it really matters, again, in these restore and auto-grow scenarios. So this next slide is very interesting. This is a great example of us not just trying to take a look at hardware trends that have existed the last few years and catch up to them, but get ahead of new hardware trends. So if you think about the evolution of storage devices, hard drive systems and newer SSD drives, you always thought in terms of maybe milliseconds for disk latency. How long did it take to write to this disk? Well, it may have taken like 8 milliseconds or 10 milliseconds. Or on the older SSD drives, maybe 1 or 2 milliseconds. If you take a look at PCI technology, PCI SSD cards, the laptop on the machine I'm presenting on right now has a PCI card in it. It looks like a memory card with little memory chips on it, but it's actually a drive. And the latency of some of these technologies can be in terms of, this symbol means microseconds, so even less than a millisecond. Well, that's interesting, and it's nice to have this technology. But in the case of write log waits, which are delays and latencies on writing the transaction log, I want to make sure that I get the fastest drive possible for transaction logs when that's my bottleneck. And if you think about the OLTP scenario, the transaction log could become a bottleneck. Even if you're using in-memory OLTP, we still have to have the transaction log for durable memory optimized tables. So I want to try to make sure that write log wait is as low as possible. And a PCI SSD card could be your answer to do that, but sometimes those are limited in size. So some of your drives, maybe you're using like a SAN, for very large log management or data management, you have these larger drives that are not going to have microsecond latency performance, right? So what are you going to do about this in these scenarios? Well, along comes this technology called NVDIMM, and this symbol means nanosecond. It's also called persistent memory, and I've got some links for you to look at this later. So these are hardware technologies today at not very big sizes, like 8 gig and 16 gig in size. And Windows 16 supports actually recognizing these drives. And you could take a drive like this 8 gig or 16 gig drive. That's, again, it's like a memory chip inside your server, and you could make a drive letter out of it. Well, you may be saying to yourself, well, Bob, that's not a big enough transaction log for me. I can't use that. Well, that's okay, because what Windows also supports is this concept called direct access. And SQL will support its concept. So here's the idea. With Windows Server 16, you would format your NTFS volume on one of these NVDIM devices with this special DAX parameter. For SQL Server, you would actually create a second transaction log file on this new volume. So imagine you having your larger transaction log on your normal SAN system. The second log will exist on this new special NVDIM smaller drive. What SQL does, and we get very intelligent when we recognize this, we'll take what's in log cache when we have to flush it, and we'll write it first to this NVDIM drive. The log cache is not going to be that large. It could easily fit on one of these drives. So we'll take the log cache, we'll write it to one of these special drives, and then lazily we will write that to the normal transaction log. And since it's persistent and can survive server restarts, you never lose any data from write logs. Now, write log wait could become 0 milliseconds. In fact, here's a funny story for you. As we were testing this technology, we were looking at one of the DMVs, which is called DM exec requests. It's got a column called wait type and wait time. And we were noticing write log would have a wait time of 0. And immediately somebody thought it was a bug. But the problem is that column is an instrument and measurement of milliseconds. So what was happening is we were getting write log latencies in microseconds. And we didn't even realize it. So again, a really cool technology to keep up with evolving hardware trends and make things run faster based on the technology, and SQL taking advantage of it in a way that still gives it consistency but also with performance. I've created some great links for you to take a look at later. And in SQL 17, we've actually created a new syntax to support telling us specifically where is this persistent log buffer. Instead of just creating a second file, you will actually tell us, create your normal log file and just tell us where is your special persistent log buffer based on using this technology. And what I've seen, as I told you, this PCI card in my laptop's pretty fast. We even see 2x speed performance even faster than that technology itself. So again, persistent log buffer, a great example of us keeping ahead of what's going on in today's technology. And there's a really nice blog post by Kevin Farley, one of our lead program managers on our team, that go into the architecture details of how we put this together. All available by just using Windows Server 16 and then using with one of our hardware partners that support this technology on SQL Server.
Bob?
Yeah.
Question. You're talking about the log buffer of 60K per database?
Well, the log cache itself, as you know, is not that large. And I forgot the exact sizes that we put in log cache. But it easily fits in one of these NVDIM drives.
Okay.
Yeah. So again, think of the log cache being a certain finite size that's much smaller, but your actual transaction log being obviously bigger. So we're just effectively taking the log cache when you say commit, writing it to the special drive. We come back to the application and say, you're good. And then we lazily write it later. And even if SQL had to restart, this is persisted on a disk, right? We know how to go take that and apply it to the normal transaction log before we run recovery.
Yeah. You have another question?
Did you guys have another question?
Yeah, go. Just a minute. דרש אותי, אין סיכוי שאני קודם, לבוא לפה. קיבלתי אותך פה מזמן. בוא תשאל, נו.
השאלה פשוטה.
כן.
השאלה פשוטה.
Sorry, Bob.
It's okay.
זה כל רפליקה, יותר כשמורידים את הפרמטרים, אז אין שום בעיה עם שאילתא של הפרמטרים. מעלים אותו, זה נועד, זה איזושהי
Okay, so the question is about the parallel redo on a secondary replica.
The parallel redo?
Yeah, on a secondary replica. And,
okay.
Availability group. When the parallel redo functionality is on, when it's off and you have a parallel query, right? Then there is no problem. When the functionality is on, there is a problem with file application. The problem is, what is the problem? There is a schema shared log.
Yeah, when we do parallel redo on a replica, we do have to have synchronization to the data, right? So anybody running like on a read-only replica, it is fair that when we're redoing this data, we have to have some synchronization with the queries that are running. So I've not seen significant slowdowns from that. There's been a few issues reported from some customers, but any of those issues have been resolved with our latest updates for Service Pack 1 and 16 and our cumulative updates. But there is some synchronization that takes place with the parallel redo threads on a replica in a read-only scenario and the queries that are running. Any issues that I've seen that we run into, we've addressed all those. Okay. So I know we have about 5 minutes left here, so let me cover a couple of topics at the end to kind of finish off the discussion. And one of them is called Windows Functions. And I shamelessly use the Windows logo. This has nothing to do with the Windows operating system. It's something called a Windows function. And if you've never seen it before, this is kind of the example of one of these queries with a Windows function. When you see this over syntax, if you're in a scenario where you're running analytic type queries, and you're always doing aggregations, group bys, and so forth, it can get pretty frustrating to have like multiple queries, multiple aggregations, limitations to the T-SQL syntax. So if you're in that scenario, please look at the resources for something called a Windows function. It allows you, in a way, to look at partitions of data, multiple partition data, and aggregate it within a single query. And again, use this over syntax as a special T-SQL syntax to do this. And so it's worked for several different versions of SQL Server, but we took a look at that technology and we combined it with column store to make things faster in SQL 16 by default using a concept called batch processing. And look at this chart right here. This chart's a very interesting chart. So the orange chart represents what is the speed as we create more parallel workers on top of one of these queries without using Windows functions, using this concept without a column store index. So you can see you get to about eight or so or 10 processors and you kind of max out a performance and you kind of flatten out. So it's not reverse scalability, but it certainly isn't scalability. You want to see a chart that looks like this blue one. And so what we were trying to do for big analytic queries for these Windows functions is push the processor as hard as we could. As you create more parallel workers, we wanted to get faster. And we've achieved this. So taking these Windows function technologies, these queries you've been using for Windows functions on SQL 16, and simply by using a column store index, and it's by pushing it on a hard processor a lot of cores, you can achieve really incredible performance. We don't have time to go into the demo, but I've created a demo for you to have that you can use. It's a demo using simulating a website's click stream to analyze the number of clicks that happen on a website. And it's a very interesting demo if you take a look at. You know, set up the database, doesn't take that long, you do it on your laptop, and then run the row speed versus batch speed that you see with and without a column store index. And what we've done is we've introduced a new operator called a Windows aggregate operator that allows you to do this batch processing and achieve these kind of type speeds. So a great example of us taking a function that's used by a lot of people in analytics, and by combining column store with this batch processing, really pushing queries at a very high scalable level. Let's finish the talk with availability groups, a very popular topic for a lot of people. And what we noticed in the SQL, we introduced this technology in SQL 12 as an evolution of database mirroring. And what we noticed in SQL 14 is customers coming to us with these faster I/O systems and saying, hey, what happens is I put on a sync replica and my performance of my app on my primary goes way down. And we discovered that in our case, in several situations, it was our code that was causing the bottleneck, not the I/O. Because before, when people had slower I/O systems on the secondary, we could always point to the I/O and say, well, it's your I/O. The I/O is slowing down the sync, so you got to fix that. And then customers say, fine, I fixed that. I put the fastest I/O system in the world on primary and secondary, but I'm still slow. And so we took a hard look at ourselves and our code and discovered we had bottleneck problems. And so we came up with some new ideas. We said we wanted a goal that if you've got the right hardware in place, we can be 95% of standalone speed with a single sync replica. So in other words, if you ran your app with no replica, you could put on a single sync replica and you get 95% of the speed you could without the replica. And we did all these types of things to look at. Like one of the number one things we did is to just take a look at the number of thread context switches involved on the primary and secondary to do all this work. You know, to harden the primary log, to package up the data, to send it across to the secondary, to harden the second log and send the results back, right? Because that's the sequence of a sync commit. And so we reduced all of that. We changed our architecture slightly. We introduced this multiple log writer concept I mentioned. We used this parallel redo concept. And then we even did things like reducing spin lock and tension. Or we would even improve the communication path. We could take the log writer task responsible for hardening the log of the primary, and if the hardware could keep up on the secondary, we could directly from that code send the data. As long as things could actually keep up, there's no reason we couldn't do things like that. And what we're able to achieve, and this is all public information, in fact, I created a blog post on this, is this chart, and let me explain it. So what you see here in the blue line is the standalone workload speed. So this is the log throughput on the primary. These are the number of concurrent users that you would have you're pushing your workload on. So the harder you push, you want this thing to scale. And you can see the blue line shows the scalability you would achieve. The yellow line, unfortunately, represents SQL 14 and its ability with a single sync replica. So the gap is enormous between the blue line and the yellow line, especially. See, early on, there's no gap, but as you push number of users, this just gets crazy. Well, I'm proud to tell you that with these hardware specs that I've got listed over here on the left, the orange line represents what we've achieved in SQL 16, which is 95% of this blue line. And the gray line represents here with encryption. So even with encryption, we can get 90% of that speed. And this is all in by default. You don't have to make any changes, provided that you've got the right hardware on the primary and secondary. And again, this is not that expensive of hardware I've got listed right here. You can make this kind of scenario happen. And that's our pitch for Always On, that we want to make sure that you don't sacrifice the choice of HADR and that it has to totally sacrifice performance of your primary application. So I just want to quickly mention that we have migration tools for you. If you're thinking about moving to SQL 16, we have all sorts of tools for you to use to be able to do that. One tool you might not have played with before is something called Database Experimentation Assistant, which is in preview and downloadable. The concept being where you capture a actual replay of your production workload, say on a SQL 2008 instance, then you'd replay it against both your 8 and 16 instance. We can compare your queries. The Database Migration Assistant just compares your configuration, but Database Experimentation Assistant compares the performance of your queries across SQL instances. So take a look at those technologies. We've got a new Azure Database Migration Service, which helps you, which is a really big, interesting service if you're thinking about moving to the cloud. If you're making cloud decisions, take a look at that as well, even from third-party database products. And then, SQL 17 is imminent. We've been working this pretty hard, and we're pretty close to getting. We just released release candidate 1, and I have a lot of people ask me, the SQL 16 It's Run Faster talk is really interesting. Interesting features you put in the product that aren't so noticeable. What are you doing for 17? Well, coming soon is this new concept called the Fast and Furious. So at the Microsoft Ignite conference, which is here in Orlando, Florida, at the end of September, I will be announcing this new branding that we have for what we put in SQL 6.17, both in the experiences of running SQL Server on Windows and SQL Server on Linux in both environments. So nothing to show today because I don't want to give it away, but end of September you'll see that, and you'll see a lot of information I'll provide post that conference and blog posts and various things. There'll also be a talk at the PASS Summit end of October on the same concept. So that's the next evolution of this series that I'm doing. We have more things that we've blogged about that I even covered today, and we have some things that we haven't even really, quite frankly, had a chance to research that we know we could talk about that could enhance performance of your application. So that is really the end of the talk. There's some resources for you. Again, aka.ms/bobwardms has this deck that I'm talking about right now and has the demos that I use. And I really promise you, if you'll go run that demo, the initial one with dynamic memory response, I've run that hundreds of times on this laptop. There must be something on my configuration page to work. You can easily see the differences that I've developed. I realize I'm 4 minutes over. I apologize for that, but I want to make sure that before you leave today, because you've all been so nice to stay over in your evening at home, that I answer any questions you have.
Right. Question? Regarding parallel redo, is it possible to control the number of threads in parallel redo?
So in parallel redo, no. You don't control the number of threads. There's no max degree of parallel setting. We control the number of threads. So we decide based on number of cores that you're running on. So in that particular example, you saw that there were 4 parallel redo workers running. I had a single core machine with I had a single processor with 4 cores. So for any given database, we will not spin up any more threads than cores in your machine. But as I mentioned, there's a max. So we'll only go max of 16 for a database or a total of 100 for the entire instance as we're doing redo.
Okay. Question? No? Thank you very much, Bob.
Well, I really appreciate your time today. Thank you very much.
Thank you, Bob.
Thank you.
We'll see you in April in SQL Saturday in Israel.
Yeah, that's great ideas that you wanted to visit Israel. Maybe you
when is SQL Saturday in Israel?
probably in April.
In April. Okay.